starting the presentation. And yeah, so for those of you who have not seen me before, I'm Thomas Jansen. I'm the chair of the computational spectroscopy, and I'm also director of the Top Master Nanoscience program. So, and I'm the first examiner or the supervisor of Teun Zijp. And the other person I would like to introduce you to, he just unmuted his camera, so that's Remco Havenit. So he's going to be the second examiner. So he read the thesis and he's going to join today and help grading. And he is also the head of quantum chemistry, right? And he's also teaching quite a bit actually in the Top Master program. So if there's something with electronic structure, then Remco is the expert. And then I think the third person to introduce is today the most important one, because that's Teun Zijp. And he's going to talk about today about his research he has done over the last a bit more than a year in our group, and he's been working on making it possible to see transport in 2D spectroscopy, a new type of 2D spectroscopy, but he's going to explain that to you in detail in a moment. Just one more thing before we start, I would please ask you all to please mute yourself during the presentation, and we will take questions at the end, because otherwise it's quite complicated for such an online presentation. And if you want to ask a question, indeed, you can just raise your hand at the bottom of your screen, or I think you can press H maybe on your screen, and then it will ask the question. Exactly, Peter. Now everybody has to test this. So without further ado, I would like to give the word to Teun. So floor is yours, Teun.
Thanks a lot. Today I wanted to talk about how do we see exciton dynamics or exciton transport in antenna networks with 2D electronic spectroscopy. And to give you a clue on what this approximately looks like, we have a pulsed laser which we shoot at an antenna network, and as a consequence, we get excitons. These excitons, they will migrate inside this light harvesting network, and that, as a consequence, will generate a two-dimensional electronic spectrum. And I will explain all these parts in more detail. We have a table of contents. So first, I will discuss photon systems in nature, and I will introduce double-sided Feynman diagrams. I will talk about the pulse sequence, and then we can finally see the exciton dynamics. And I have small and big simulations, and they also have huge systems to reach a conclusion. So let's start with looking at nature. Actually, I want to go a bit back in time. Maybe this is a bit too far back in time, but I want to look at the beginning of photosystem 1. And well, the first bacterium was actually a chemotroph, so it was eating chemical soup from these thermal vents on the bottom of the ocean. But in the sea, there is a sea current which exchanges the population from the seafloor to the top layer of the sea. So some of these bacteria can migrate or will migrate from the seafloor to the top layer. And in the top layer, we don't have this chemical soup anymore. But so the bacteria needs to learn to get its energy from a different source, and has learned to eat sunlight or do photosynthesis. And this is actually what one of the first, I think the first photosynthesis bacterium can do, and it's called the green sulphur bacteria, or also the GSB for short. But then we again get these seed currents, and we can exchange top layer with the bottom layer again. So as a consequence, the green sulfur bacterium, which has evolved of the ocean, will now end up on the bottom of the seafloor again, near these thermal vents again, and they glow a bit. But it's very dim, but there is light, and now the green sulfur bacterium has incentive to evolve even further to optimize its light harvesting antenna to collect photons from this very dim light source. And as a consequence, we get very efficient light harvesting from these glowing thermal vents, which I think is a very cool way of evolution. So this is how the evolution tree looks like. Daddy, where did photosystem 1 come from? Well, there are a lot of bacterial species. So we have the green sulfur bacteria, the antenna in the light harvesting antenna in spinach. We have algae over here, and here on the bottom we have purple non-sulfur bacteria, and here we have cyanobacteria, and they are all genetically related. So even though the photosystems look very differently, they are all genetically related, and they have a common ancestor, which is very surprising if you look at these photosystems. For example, the light harvesting antenna in green sulfur bacteria is a chlorosome, while for algae and purple non-sulfur bacteria, the light harvesting antenna is these disc-like structures which are embedded inside a membrane, and they form this, and my supervisor and I call this pizza. This looks like pizza with the olives and the salami, I guess. But there's also the photosystems in cyanobacteria and spinach, which again looks way differently. But they all have the same purpose, to catch light and bring it to a chemical center. So the antenna networks that I will be looking at are embedded in the membrane, and it's photosystem 1 and photosystem 2. I will explain in a bit. So it's these networks. Here we have photosystem 1. That's the blue with the red. The red is the reaction center. So that is where the photon energy is converted to chemical energy. And then the other green things are all light harvesting system 2, which are only there with its only purpose to catch light and pass it on to LH1, which will bring it, convert it to chemical energy with its reaction center. And we can do a bit of, we have already done quite some, not me, but the scientific community already has done a lot of spectroscopy on LH2. So you can see the absorption of B850, which is these red rings, and the blue over here, that is B800. These are different molecules which will harvest the light in different parts of the spectrum. Now I want to introduce double-sided Feynman diagrams. And again, let's look at this picture. So we have absorption. The absorption by looking at either the bra or the cat, and we look at the interaction. So if we have a photon coming in, we will get coherence with one of the excited states in the medium. And this is very important. But in order to get absorption, we of course need to have overlap between the ground state and the first excited state. Sorry, this energy difference needs to match the spectrum. So that is very important. We can have transmission, which is on the left, the left diagram, or we can have absorption, which is the right diagram. And we will see in a bit that this is very important for more complicated Feynman diagrams. This is a more complicated Feynman diagram, but I think it's also very a very important diagram. In the ground state, which is indicated by 0, 0. And let's put on the laser pointer. So we are in this state. And then we have a laser pulse, which brings the cat in the first excited state. So we are no longer in the full ground state. We have oscillating wave inside our molecule. Then the second pulse comes in, and we are in coherence with the cat is in coherence with the second excited state. And subsequently, our system can emit a photon with twice the frequency of the first excited state. And this sounds very complicated and very magical, but it happens quite fast, and is commonly used in these green laser pointers. So here we have a frequency doubling crystal. So this is a very common Feynman diagram that you find in your everyday life, even though you might not notice. But the Feynman diagrams I will use for my master thesis are, well, there are more, and they're more complicated. But the key to keep in mind is that we have coherence in the first time interval between the first two laser pulses, and this, if we take a Fourier transform of the first time interval, we get ω1, and we have well, between the third and fourth pulse. Sorry. No, 1, 2, yeah. No, we have oh fuck, I don't know, but we have a T3, so a third, sorry, another time interval, and if we take the Fourier transform of the third, we get ω3, and if we observe a photon when these two time intervals are in coherence, a dot in the middle of our screen with that we collected photons on that so now I need to discuss these pulse sequences with you, and I will go through the Feynman diagram a bit more slowly. So we tilted at we basically tilt this axis and look at it. So this is our first pulse, and sorry, this is two-dimensional electronic spectroscopy, and this is what we will get out. First pulse introduces polarization in our medium, and it will generate excited states. And I will represent this with running stick figures. So if we have the first pulse coming in, we will see that the runners start running. But the second pulse will bring it to its full excited state, and full first excited state. So both the bra and the cat are in its first excited state. Then we have a stationary state, so there's no fast oscillation anymore. We are pausing the animation, and then we with the second pulse, and then we have the second time interval. And in the second time interval, we can choose how long it takes, the second time interval. But what basically happens is that the local environment of all the molecules changes a bit, and this will cause the molecules to change frequency a bit. And this I will represent with that the runners will change color. So let's say that we have this change of color, that red becomes blue, etc., etc. And then we have our third pulse coming in, which will start our runners from running again. Well, there are two ways that the runners can run now. They can run in the same direction with the same phase. Then basically, well, we have more dephasing, so non-rephasing. But we can also have that the runners start running in the opposite direction. And if we do that, then we can see that there is a new, or the polarization which we initially had is recreated, is returned. And this is in a 3-pulse electronic spectroscopy experiment. What we do, we then collect this collective oscillation as stimulated emission, and we call it the measurement. This is when we collect our photons. But the problem is that we collect this with a laser pulse. So we have the laser frequency here, the blue dashed line, which is, of course, because it needs to be it needs to resonate with the states which are present in the medium. So the B800 and B850. Because of this, the laser pulse will always overlap with the emission line. So we have a lot of noise relative to the signal that we are trying to collect from the stimulated emission. Now, there is someone in Michigan who invented a trick to increase the signal-to-noise ratio, and that is adding a fourth pulse. And the fourth pulse will stop the runners from running again, so we get back into a full excited state. And that's what we observe in this animation. And what we then basically do is wait and collect the photon, because all the excited states which are present in the medium then will emit one photon. But it will be later than the pulse, or we can measure this after the pulse is gone, so we don't have the noise from the laser spectrum. So we have a higher signal-to-noise ratio. Of course, this signal will decay over time, so we have to be fast, but the signal-to-noise ratio is still way higher, and this is good news for our sample, which is, of course, optimized for dim light. So we don't need to put a very intense laser on these photo systems, which are optimized for dim light, because they will photobleach instantly. So this is the explanation for the fluorescence detected two-dimensional electronic spectroscopy. And this is a very new technique. Oh, sorry, I will explain this in this slide. So we have the 3-pulse experiment, which is relatively old, but it's well understood. But unfortunately, it has a low signal-to-noise ratio. Now we have the 4-pulse experiment, which is new, and it has a high signal-to-noise ratio. But it's because it's so new, it's still poorly understood. So here we come to the goal of this thesis. It's to better understand fluorescence detected electronic spectroscopy. So this is what I would ultimately like to understand. And then we need to take a look at these Feynman diagrams. So these are the Feynman diagrams with 1, 2, 3, 4 pulses, and then we wait and collect the photons which come out. And we have the rephasing diagrams, which will these kind of signal, and we have the non-rephasing diagrams, which will give rise to these kind of line shapes. It's called line shapes. Sorry. So these kind of experiments are already done on light harvesting system 2, and we can very well see the diagonal peaks and the cross peaks and the other diagonal peak. But for harvesting networks, so where we have both LH2 and LH1, but this is not done yet. So we still don't know how to look, and there's a lot of things that, well, can go on. We basically want to get a better understanding, especially because in the excited state absorption 2 diagrams, we will have 2 excited states. And there will be something interesting with these light harvesting system if we have 2 excited states. Because, okay, we have our first pulse coming in, generating 1 excited state. We have, well, then we have some diffusion, of course. And then we have the second pulse coming in, generating another excited state. And then, of course, we have migration. But sometimes it happens that these 2 excited states end up on the same molecule. And we, when these 2 excited states get to the same molecule, a higher excited state is generated, typically the second excited state, or at least I think so. And this excited state decays very fast. So it decays to the first excited state without emission of a photon. So we lose photons. It's a photon quenching mechanism. Yeah, this is something we really need to take into account. So now we need to go over all these diagrams one by one, and we need to see what is the signal intensity from all these diagrams. So this is the Feynman diagram for the ground state Bleach, and well, there are 4 pulses, and we can have either that the T1 is in coherence with molecule A. Molecule A, by the way, in these graphs, I still have used the B800, B850 settings, but of course, A and B could also be theoretically LH1, LH2. And we have we can also have cross peaks, so that we have coherence with molecule A during T1 and coherence with molecule B during T3. So then we observe these peaks. Of course, A and B can be interchanged, so we can also observe this diagonal peak and this cross peak if we interchange the A and B in these diagrams. And we have stimulated emission. And well, if you fill in the numbers, then you can see that we only observe coherence with molecule A in both like in both T1 or T3. So we will only observe diagonal peaks. Well, you can do the other diagram to make coherence with molecule B in T3, but then we get the BA state, which is a non-stationary state. So this is not a full excited state, and it will generate oscillations in our medium, depending on the time interval T2. So we will get, well, if there are questions about this, I can discuss this in after the discussion. Sorry, after the conclusion. but for now I will simply skip this because it's not a long-lived state because we have the dephasing. Yeah, so if there are questions about this, then or if someone is interested, I can talk more about this. But first, let's go on because we have more diagrams. We also have excited state absorption 1, and well, here we have the overtone peak, which is in coherence with A2 minus A. And these are higher in energy, they oscillate with higher frequency than the normal diagonal peaks. So here the gray line is the diagonal. But we also have cross peaks. And we also have that the cross peak also beat, just like in the stimulated emission diagrams. We also have excited state absorption 2 diagrams, and they look a lot like each other. But the main difference is actually that the number of pulses on the cat. And so in excited state absorption 1, we have 4 pulses on the cat side, and in excited state absorption 2, we have 3 interactions with the cat side. And the sign of a diagram is proportional to, the sign is equal to -1 to the power n. So as a consequence, the sign of the other, excited state absorption 2 diagrams is opposite. So here the color, I didn't add the color bar, but it's basically the inverse. So this is 0 and this is negative, whereas this is 0 and this is positive. So if we add these two together, okay, let's first do it a bit in our head. So we have the intensity of one molecule in excited state, molecule A in excited state, minus the intensity of the second excited state. But because the second excited state is so shortly lived, this will decay very fast, and we basically have, we barely get any signal out because it's basically the same thing. It will basically become 0. Then we also have the cross peak with intensity, of molecule A minus the intensity of molecule A plus B. And the same holds for the beating cross peak term. So it's also intensity of molecule A minus intensity of molecule A plus B. And if we numerically solve this, then we see that the overtone peaks already basically disappear. And this is no surprise because second excited state is very short-lived, so this will decay very fast. So this is basically becoming 0. And we do observe the cross peak, and we still have the beating term for the cross peak. So if we now want to look at the cross peak intensity, we have these diagrams, which give the permanent contribution. So with that, I mean T2 independent, so it's not beating. And for so we have A plus B minus A plus B. So the intensity of emission of molecule A plus the intensity of emission of molecule B minus the combined emission. And when we have 2 excitons in the model, we cannot, we need to solve this with the kinetic model. So now we need to look at the light harvesting system. This is how it looks, but if we look at it from a perspective of an exciton, you basically see this. Oh, sorry, I didn't check this slide. But either way, we basically see that we can either have, the exciton can move around on this. And if we have two excitons on this network, then we can move around like between all these four states, and we can have annihilation on either of all these molecules. So let's look at a smaller version, a smaller model. Let's first look at only LH1 and LH2. So we have a dimer of molecule A and molecule B, I will call it for short. And we can have well, two excited states, but then one excited state will move to the other, one way or the other, but the rate from B to A is greater than from B to A to B. So we mainly get this path, and then we get the second excited state being generated. And the second excited state will decay very fast towards the first excited state, so just A. And this will fluoresce over time relatively slowly to the ground state, and then we get the fluorescence. So that is how we usually read this kinetic model of a dimer. But yeah, then that's only a dimer. We can actually almost like analytically solve this. So this is what I did in Mathematica here. And then I installed some photon counters. But this is just part of the timer, and it's just to make the graphs of which I already showed you. But we actually want to look at bigger simulations. So these are the light tungsten systems which we encounter in nature. So there's more than two molecules, and we can no longer solve this analytically. So we need to numerically solve this. And I will do this using a matrix, but most matrices are squares, and a square has four neighbors. But one light-Hersing system, however, has 1, 2, 3, 4, 5, 6 neighbors. Yeah, well, again, I guess nature has hexagons, which are vestigons. But yeah, so we have to apply sort of a trick to make squares more hexagonal-like. The trick I used was, well, we can have these 6 ways of interacting with your neighbor in the central hexagon. Central hexagon. And the trick I apply is basically making the upper, the left up, and the bottom down elements in these square matrices interact as well. So then the squares also think that they have 6 neighbors. And if we put this in code, then we just put some line of code to make sure that these diagonal neighbors also interact. And then we can already do a simulation on a grid. This doesn't work for 2 excited states though. And I can explain a bit more about the code if you have questions about this, but if not, I would really like to convert the grid to a vector. Oh yeah, maybe a bit of explanation in grid, because I use a simplification. 0 means wall, 1 means LH1, and 2 means LH2. So now I just have a matrix with 0, 1, or 2, and then that is my light-Hersing network. So if I compare this to a vector in which I only have the states, the first, where element 0 is the full ground state. And after that, we get A, B, C, D, and then we get the double excited states. So if we have the double excited state of 1 excited state on C and 1 excited state on B, then we will have a population vector in which the element number 8 is as a 1. And we can convert this to one time step in the future by multiplying with its K matrix. and I have a computer code which will generate this K matrix for me, and then I know the situation after a certain number, and I can apply this time step matrix many times to see how the system behaves after a number of time steps. So that's what I did over here. And here I only look at one simulation at a time. But then I thought, let's take matrix powers. Let's not multiply with the population factor, but instead let's look at the entire matrix at the same time. So in Python, we can impart the matrix power function, and then we can look at the k-grid after n time steps. So that's what I do over here. This is how the k-matrix evolves after n time steps. You can see that the population moves around in these matrices. And after about 10 nanoseconds, or I use 5, then, well, basically we have converted all the excited states to the ground state. So you can read it as we start from this state, and in the end we end up in this state. And we also have the photon counters over here. So then if we do a bit like slightly bigger simulation, we now have a trimer, so 3 molecules, LH1, LH2, LH1, or this one. But then we can start to compare 2 simulations with each other. And, well, there was too little difference between these simulations to actually tell you anything about it. But I do want to show you the way how I will calculate the ratio between cross peaks and diagonal peaks, because the intensity is related to the mu, which is the dipole. But we can just simply tell the computer to look up the appropriate numbers in this k-grid after n steps, and then it will generate calculate the ratio between the diagonal peak and the cross peak, or sorry, the cross peak with the diagonal peak. So the cross peaks are about a quarter of the diagonal peak intensity. And we can do this trick for way bigger systems. And this is an animation of the k-grid for the biggest system I could fit on my screen. And I thought this looked quite impressive. That's why I wanted to show you. But of course, no human being will ever look at all these numbers. That's why we use the computer, and we teach the computer to only look at the last column in which the photon counters are present. And then we can convert these numbers to cross peak to diagonal peak intensity. And here I did a trick in which I looked at the distance of of the left LH1 with the second excited state. So if I put the second excited state further and further, do I see a change in the diagonal peak to cross peak ratio? And actually, we do see a change. And there is also, so if we only have LH2, LH2 is very good at conducting the excited state, so it will move it from here to there without problem. So that's what we see in the red lines, very steep. Then if we introduce more and more light harvesting system ones, these are like magnets. They attract the excited state, or you can also see it as a speed bump, because here it will be like we will get accumulation of the excited state over here and over here, and it will not be transmitted that easily. But if we look at the last simulation with 7 excited states, sorry, 7 not 7 times an LH1. Well, we have a bit of leakage from LH1 to LH2, and from there we have just as much exciton that will move back to the first LH1 as to the left LH1. So here it's actually more conductive, and that's why you see that the purple line is on top. I see that I'm slowly running out of time, so I have more simulations, and I thought, okay, maybe we can avoid the exciton annihilation if we add more LH2 to the network, so that the excited state can move more around, more degrees of freedom. And that wasn't really the case, and we did get these really weird sawtooth patterns. Then I decided to look at squares because I could make these more symmetrical. And then I decided, well, you know what? Let's calculate all the excited states combinations. So I could just say, okay, look at all the double excited state combinations that you can find, calculate its distance, and then we can make this plot. And then we see, well, we can see sort of a trend, I guess. Well, it's a bit hard to interpret. Eventually, I ended up, because this is an experiment which we cannot do in real life anyways. I just put all the data in one column, and I calculated the mean and the average. So then, if we look at LH2, we see that if we add more and more LH1 to the simulation box, we see that the cross-peak intensity drops. So we get more, we get less cross-peak in general. But this is only with 6 simulation boxes, and I mean, this is maybe not so significant. So I decided, you know what, I need to do a bigger simulation. I need to do more simulations. So I generated up some code which will generate random simulation boxes, and each simulation number we add a LH1 to the system. We incrementally increase the number of LH1, and we basically replace one LH2 with an LH1. And after that, we also create vacancies. So here I've called it LH0 because it's a 0 in the grid. So then we create vacancies, and we artificially increase the concentration of LH1 even further. And if we look at the, I've only given 9 of these configurations because, of course, there are 36 or 35 of these simulation boxes. So if we look at the cross-peak intensity, we can indeed see that the trend continues. So we still have more, we see that there's less and less cross-peak intensity if there is more LH1 concentration. So my conclusion is that we now understand fluorescence detected two-dimensional electronic spectroscopy slightly better. We can look at the we know the Feynman diagrams which are relevant. We can predict which spectra these diagrams should make. We know the intensity formula for these peaks. We can do a simulation, and then we can find the cross-peak to diagonal peak ratio. This is what I've done for my master thesis. But we could also, I've only looked at LH1 and LH2. You could also do this for other systems, and they don't even need to be natural systems. We could also look at, like artificial light harvesting systems like solar cells. We can also do a similar exciton dynamics simulation. So maybe the model I have developed could also be used in other systems. But yeah, this is just an outlook. And yeah, this was my presentation.
Thank you very much, Teun. So we are open for questions, and I think Peter is the first.
Okay.
Yeah. Do you mind if I ask a question?
Yes, you can ask the question.
So the first thing you said was, in case there are two excitons in your system, you'll want to use a kinetic model.
Yes.
Why do you choose that over any other type of propagation?
How do you mean?
Well, I assume that there are multiple ways of propagating your system, of finding populations over time. So why would you go for a kinetic model in that case, and not something maybe quantum mechanical?
I think that quantum mechanics is very difficult, especially for these systems. I mean, we have here we already have, how many molecules is it? I counted them somewhere. We have 36 LH2s and 7 LH1s. So we have 43 light harvesting complexes. Well, I think that doing the quantum dynamics in one light harvesting system is already complicated and might already take a day or so. But if you include this many atoms, I don't think that your simulation will be finished before the end of the universe. I mean, it's not crystalline. It's not a repetitive structure. Everything, like there's asymmetry. There's the distances between these entities is not the same everywhere. So I think it's just quantum mechanically impossible to do. But yeah, okay. That's just what I think. You know, my supervisors agree.
But do you think you're justified in using a kinetic model rather than? So do you think you would be able to see any quantum mechanics at this scale, or do you think the kinetic model should produce the same effects, same results at this scale?
Well, I think that the quantum mechanical models are more relevant when you do a 3-pulse experiment, because then everything is moving in the last frame. But for the 4-pulse experiment, everything is stationary in the last frame. So I think that it's justified for the fluorescence detected to the spectroscopy to use a kinetic model, because we don't actually have the vibrations anymore in the system after the 4th pulse.
All right.
I think.
So I think also what you see in the experiments, right, where people have measured the transfer between light harvesting systems, they always get a rate, yeah. So that suggests that it's incoherent transfer between two LH2s, or between an LH1 and an LH2. So from that, it's probably justified.
Yeah, all right. I saw from the time scales, it's also pretty long. So the coherence would probably die.
It would probably die. There's discussion about this in the literature, but yeah.
Right. Thanks.
Yeah.
Other questions? I see Remco has a question.
Yes, you have now done many simulations
Yes.
on LH1 and LH2. And what did you learn on LH1 and LH2 complex from these simulations?
Sorry, what did I learn from the LH1 and LH2 complex?
Yes. Or could you do everything with something completely different, not LH1, LH2, but we could just call it molecule A and molecule B, not specifying the molecule?
I think I can. I think the code is very general. Of course, we will need to add in different rate constants for different systems, but the theory is quite general. Yes.
Okay, but was there also something that you wanted to learn about this light harvesting complex?
Yeah, actually, I thing I wanted to learn was how connected all these light harvesting systems are. So how fast can we get from one end of the simulation to the other end of one end of the simulation box to the other end of the simulation box, and how much excited state would be lost and stuff like that. But that is something which I can study with this one.
Okay, but you don't have the answers yet.
No, I've only focused on things which could be measured, rather than on things which could be theoretically possible, could be theoretically interesting.
But still, you did conclude, right, that for this kind of systems, you would be able to see changes or variations in the cross peak depending on the composition of the sample, right? So
yeah,
while the experiments were not done, the experiments would be providing valuable information, right? So
yeah. So the less cross peak we observe, the more annihilation we have. So the more the light harvesting systems are connected. Wait, does that make sense? No. Oh, wait, maybe that doesn't make sense. I need to think about this.
I think you turned the argument. The more annihilation,
yes, you're right.
The more cross peaks you have, yeah?
Yeah, the more annihilation we have, the more cross peaks. The intenser the cross peak will be observed. Yeah, that's true. Yeah, sorry. Yeah, that was my bad.
Can I ask something on this particular
question?
So now when you're saying that the intensity of the cross peak is mainly connected with the annihilation, but isn't the intensity of the cross peak also connected with some other dynamics in your system, or only with the annihilation?
No, I think in my simulation it's only with the well, yes, okay, of course there are small fluctuations for the cross peak intensity as well. No, wait, sorry. No, the other fluctuations are all cancelled, I think, because we subtract the ABSD. Sorry. This is. I wish I could answer your question more.
No. But so in your simulation, you're saying that you are focusing on annihilation. But my idea was like, if you want to compare this to an experiment, could it be that, for example, in the experiment you would have also another types of dynamics, but then you could kind of distinguish those because you know what would be the contribution of annihilation?
Well, this is one thing which is measured this is measurements on only light harvesting system 2, so it's not the same simulation, so not the same as what I simulated.
Yeah.
But we do see another effect. Here we have HL, which means high light, and this is LL, which is low light conditions. So these are very dim molecules. So I thought I would should interpret this as there is a lot of LH2, which has a larger band gap, and here's a lot of LH1. But of course, when there is only LH1 in the system, anyways, this conclusion is, and then well, you can observe that the diagonal peaks are changing in intensity, which if I compare that to my simulation, where I also call it, this is the graph for the diagonal peak ratio, and we don't see any relation. It's always 50% or the upper and the lower excited state. I think because this is because the excited state will move around a lot, so we will not. The system will not be bothered if it's excited over here or over there. It will move around anyways.
So, okay, am I understanding this correctly? In the experiment, they observed the difference in the intensity of the diagonal peaks, but you're not observing such a feature. Is that what you said?
That is what I said, but it has to do with something completely different. It has to do with the fact that under low light conditions, so when the bacteria are on the seafloor and there's very little light, LH2 changes. And that is something which I did not include in my model.
I understand. That's what I want to conclude. Maybe that's a dynamics that you don't include. Yeah.
Yeah, exactly.
Okay, I understand then. Okay, very nice, Teun. And also I like the animations. Very, very nice. The thing that you made with the runners and 2D spectroscopy, you should put it on YouTube. It's very nice.
My idea was to put the entire presentation on YouTube. Yeah.
Thank you. Any final question?
By the way, why am I not seeing anyone?
I think we took out the videos. So is there any final question? Maybe I can ask a final question, Teun?
Of course.
So if you would apply this to a very good solar cell, would you see any signal?
If you were to apply this to a very good solar cell.
Yeah.
Well, it depends on in what way your solar cell is very good, because
it converts all your light into electricity.
Yeah, well, then we don't have emission, and we
Okay.
these spectroscopy techniques are very dependent on the emission of photons. If we don't collect photons, then we cannot.
Then you cannot measure. I agree.
Yeah.
Okay. So thank you very much. So
If I can elaborate on this, maybe that is the main reason why they only did experiments with only LH2, because basically what LH1 is, it converts the excited state to chemical energy. So it basically subtracts photons from the subtracts exitons from the system, which could have been detected.
Yeah, so there are tricks there where you can quench the LH1, but these are very biochemistry tricks.
Yeah, exactly.
So how should we proceed? Maybe Remco and I will meet in another meet session. I will invite you, Remco.
Okay, that's good.
I think that's the easiest. And then, Teun, I will find you in Gather.
Okay, it's cool.
Okay, see you.
See you.
Bye.
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 Thanks, everybody.